So this week, as I said earlier, we're just going to look at two sections, 4.3, 4.4. Today will be 4.3. Tuesday and Wednesday will be 4.4. Anything we don't finish, we'll wrap up on Thursday. So I'm not gonna rush through it if we're going a little bit slower. We'll finish it on Thursday, and then there'll be a study guide on Thursday for the test on Friday. And this will be the last test for term 1. Okay, so remember, rational functions. Rational means fraction. So we're going to be looking at problems that have fractions. Before we focused on drawing them, today we're going to focus on solving them. So here's an example of an equation we might solve. It's an equation with fractions. Okay, we're not there yet, but that's kind of what we're going to lead up to eventually. So most of what we're going to do is going to be algebraically. If we run into a problem that it's really difficult to do algebraically, then we might look at it on the calculator. But I'd say most of what we're going to do, it's more algebra than it is graphing. So the first problem we're going to look at, we're just going to jump right into a word problem that we can use to solve some equations. It's going to use the formula distance equals rate times time. Okay, do people remember that formula maybe from other classes or something else? Okay. So it's basically a formula that calculates how far you've gone based on your speed and the time you've been traveling at that speed. Now it is a simplified formula, so it does assume that the rate stayed the same. So it just assumes you're going at the same speed for a certain amount of time. All right, so here is our problem. So it says Sue drove 30 miles to a train station. When she got to the train station, then she got on the train and went the rest of the way by train. So she had to drive 30 miles to get to the train station. But altogether, she traveled 120 miles. Okay, so that's all we know about the distances. The other thing we know a little about is the speed. We don't know any speed exactly, but we know that the train, on average, was 20 miles an hour faster than the car. And that's everything that we need to know to set up what we're looking to set up. So the important things, she drove 30 miles by car to the train station, got on the train, and then traveled a total of 120 miles. That's the total trip. And the average rate of the train is 20 miles an hour faster than the car. So any question on the information that's given or anything there that's not clear? Okay. So what do they want us to do? Find a formula for the time it takes to complete the trip. Now, the unknown in this problem is the speed. Well, all we know is that the average rate of the train is 20 miles an hour faster than the car. Well, we have to pick a variable to represent the speed of something. Either pick a variable that represents the speed of the car, or let a variable be the speed of the train. We got to pick one. They're going to tell us in this problem, let x be the speed of the car. So we're going to base everything off that. X is the speed of the car. If they didn't tell you, well, then it would be up to you to pick a letter, any letter you want, and then tell me what that letter means. Your two choices would either be the speed of the car or the speed of the train. You wouldn't want to let the variable be the distance because we know all the distances. Or we have enough information to figure out all the distances. So don't let the variable be distance. The variable has to be the speed. Yes?
So would the speed of the train be x plus 20?
Yes. We're going to write all that down right now. Yep. All right, so we want to find the time to complete the trip. And the time is going to be a function of how fast the car is going. So how many modes of transportation is Sue taking on this trip? Yeah?
2.
2. What's the first mode of transportation?
Car.
Car. So she's going to spend, so we'll call this the total time. The total time is going to equal the time she spends in the car plus what other mode of transportation is she taking? Train. So we need to also figure out how much time she's on the train. I guess you could say the time she spends in the train. But you wouldn't say the time she spends on the car. Unless she's riding on the roof or something. Yeah. So I think we'll go with in.
Time in the train, time in car. So in the car, in the train.
Yeah. But don't say on the car. That doesn't make sense. And then I don't know. So the time in the car, and then the time she's riding on the train. Okay. What's the formula that we have that relates distance, rate, and time? D equals what?
RT.
So D equals RT. And now, since I'm dealing with time, let's solve it for time. What would time equal? Yeah?
Distance over the rate.
The distance over the rate. So to find the time in the car, you're going to need the distance in the car, and you're going to have to divide by the speed of the car. To find the time on the train, you're going to have to know the distance on the train divided by, and what would be in the bottom?
The rate of the train.
Yeah, the rate of the train, or the speed of the train. Because distance divided by rate gives you time. And that's what we're trying to find, time. Now we're going to start to fill in these 4 things with what we know. Okay, so the time as a function of the speed of the car. What's the distance that she travels in the car?
30 miles.
30 miles. And what's the rate, or what's the speed of the car? Yeah?
X.
X. X is the speed of the car. Okay, so there's the time that she spends in the car. Now we need the time she spends on the train. What's the distance that she travels by train?
90.
90. So in all, that means all together she traveled 120 miles. She did 30 of it by car. So the rest of it was by train. So the distance on the train is 90. And we already said this a minute ago, but what's the speed of the train?
X plus 20.
Yeah, it's 20 miles faster than the car. There we go. So there is an algebraic expression that represents the time to complete the trip. You just tell me how fast the car was going. If the car is going 50, I can fill in 50 for x and add it up, and then it'll tell me how long it takes to do the trip. Any questions on how we came up with that? Okay. I think that I just copied this over. It's the same. I use the same letters. Yeah. All right, so now they want us to find some things that we did last week. They want us to find some asymptotes, the zeros, so where it crosses the x-axis, the EBM, and then we're going to sketch it, but it says find a complete graph. That just means write the window, so you're not sketching it by hand. Okay. In order to find some of these things, it's going to be helpful to take these two fractions and put them together as one. In order to take two fractions and add them up, what do you have to make sure you have?
The same denominator.
You have to have the same denominator. So if you have something like this, what's one way that you can find a denominator that's common to both the 3 and the 7? Yeah?
Using like the opposites, like multiply 3 by 7.
Yeah. Yeah, exactly. If you just multiply these together, the common denominator is 21. Well, how do you make this one a 21? Right, you multiply the top and the bottom of this fraction by the other denominator. Same thing here. How do you make 7 21? You times the top and the bottom by the other denominator. So we're going to do exactly the same thing here. So the common denominator is going to be x times x plus 20, just like 3 times 7. So it's x plus 20. And then the top and the bottom of the left fraction would get multiplied by what? X plus 20. And the top and the bottom of the right fraction would get multiplied by x. Okay, so the bottom is done. It's x times x plus 20. Now in the top, what's 30 times x plus 20? That's 30x plus 600. And now the other part you have right here, what's 90 times x? 90x. Are there any like terms I can combine in the top?
30x and 90x.
Yeah. What's 30x and 90x?
120x.
120x. You'll see why we combine them into one fraction. It's going to be easier to have them as one fraction to do the EBM. Let's do this just like that for now. Okay. All right, so now let's look at finding everything. Let's start with the asymptotes. Let's do vertical asymptotes first. Vertical asymptotes are where the denominator equals 0. The denominator is already factored. Does anybody see what number you could plug in here to make that first factor 0? 0. And when you write the equation of a vertical asymptote, it's always x equals. Does anyone see the other number you could plug in that would make the second factor 0? Negative 20. Now, negative 20 might not make sense because x is the speed, so negative speed doesn't really make sense, but that's not what the problem's asking. It's just asking us to find the asymptotes. Okay, so there's the verticals. What other kind of asymptote can we have?
Horizontal.
Yep, we can have horizontal. And to find that, we really have to find EBM. Yep. Yeah. Does anyone remember what EBM stands for? Yep, end behavior model. To find the end behavior model, you take the highest degree term in the top and you divide by the highest degree term in the bottom. What's the highest degree term in the top?
20x.
120x. You wouldn't have known it was a 120 unless you put them together. That's why we had to find a common denominator. So 120x. Now be careful with the bottom. The highest degree term in the bottom would be if you had this all distributed out. What would be the highest degree term in the bottom?
Squares.
It would be x squared if you distribute the x out. Okay, so the highest degree term in the bottom is x squared. And what does that leave me with for an EDM when I reduce it as much as I can?
120 over x.
120 over x. Okay, so there's your EDM, which is also going to give us the horizontal asymptote. To find the horizontal asymptote, you look at the EDM, and you let x, well, what do you let happen to x? You let x get to be what kind of number? You remember, yeah?
Was 0? Oh, sorry, towards infinity.
Towards what?
Infinity.
Yes. You let x get really, 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 really big, and you tell me what happens to the number in this box. So as x gets really, really big, the bottom of this fraction gets really big. So this entire fraction would get really small, and it would get close to what number?
0.
0. Yep. That is your horizontal asymptote. So we got the horizontal asymptote, we got the EDM, the zeros, okay, that's where it crosses the x-axis. All right, so let's find the zeros. What's another name for that? Graphically, where it crosses the x-axis, what do you call that? Yeah, we want the x-intercept, which is when what letter equals 0?
What?
Right, y. It's when the y value equals 0. Let's go back up and look at our formula. Here was our original problem. What's the y value there? Yeah? Yeah, t of x, right? Anything that's written with the parentheses with the letter in front, that's the y value. So the y value is, it's like it's right on that side. So if we want to find the x-intercept, what number did we just say we plug in for y? 0. Yeah, plug in 0. So you have 0 equals 120x plus 600. Divided by x times x plus 20. Now, the only way that a fraction can equal 0 is if something special happens. What's the only way that a fraction can equal 0?
Numerator equals 0.
If the numerator equals 0. What's the numerator here? 120x plus 600. That's another reason why you had to combine these together. You can't find the y or the x-intercept without putting those together as one fraction. So set that fraction equal to 0, which basically just means when is the top equal to 0. Okay, what would be your first step to solve that for x? Yeah.
Subtract 600 on both sides.
Okay, subtract 600 on both sides. That's gone. And what would be my last step?
Divide by 120.
Yep, divide by 120. That does go in nicely. What's negative 60 divided by 12?
Negative 5.
Negative 5. Yep. So this graph is going to cross the x-axis at -5. And you can check it. Plug -5 back in, and you'll get 0 divided by something. Well, 0 divided by anything is 0. So that's the asymptotes, the zeros, the EBM. And now let's do a sketch. When you sketch it, you can type in either the original problem, or you can type it in all combined together. Doesn't matter. Anybody have a preference which way we type it in? The original one or the combined one? Combined one? Okay. So let's type that in. So in parentheses, put 120x plus 600 divided by, in parentheses, x times x plus 20. That's how I would do it. So I put parentheses around the entire numerator and entire denominator. Just like this. All right. Now, we're not thinking about this in terms of the word problem. Okay? We're just thinking about it in terms of what we've got. So I know that I have a vertical asymptote at -20. So I'm going to set my screen a little further than that. Let's go maybe like -30. What else? We have to make sure we go to 0. Definitely want to make sure we go to -5. So I would say let's go to 50. All right, let's try that. Take graph and see what it looks like. Okay, so I think I'm seeing my asymptote. I'm not sure if there's something else in that lower left corner. See that little dot right there? Not sure if something else is happening over there. So what I'm going to do is I'm just going to look a little bit lower and to the left and just see if there's anything over there. Let's go -40 and let's go -30. Yeah, there was. So there's a complete graph. So we're lucky I saw that one like pixel on the screen. I almost would have missed that if I hadn't zoomed low enough. But that's basically what the graph looks like. So there's a piece that's curving in the lower left. There's a piece that's curving in the upper right. And then there's kind of this piece in the middle. Now, if we were focusing on the word problem, okay, what part of that graph would we really be kind of focusing in on? If we were thinking about it in terms of the context of the suit traveling somewhere. Yeah?
The one on the right.
Yeah, just the piece on the upper right. Because over here, this represents negative speed. It's part of the graph algebraically, but it doesn't make any sense for the word problem. Okay. So in a minute, I'm going to zoom just so I can see what's in quadrant 1. But I would say as far as a complete graph of just this equation, that's a good window right there. So I would just write down these numbers. And that was -40. So any question on graphing or finding any of the asymptotes, the EBM, or where it crosses the x-axis? That actually looks like -5, and that's exactly what we got. Yeah. Looks good.
Good question.
Yeah.
Will a lot of that be exercise because all it asks for us is find the formula with, for the time to complete the trip?
Sorry, so what's your question?
The question that we were going through was find a formula for the time.
To complete the trap.
Yeah.
Yeah, and that's what That was the first thing we did. So that
Yeah.
that's a formula for the time to complete the
So
trip.
none of the others was needed, but it's nice to know.
You mean to do the previous question? Did you need any of this
okay.
stuff?
Yeah. Did you need any of the like finding isotopes and all that?
No, not to answer question one.
Okay.
Question one was just finding the formula. Then question two was kind of analyzing the formula. Yeah. So separate, a little bit separate. Okay. Other questions? All right. So now I want to use that same formula, and I'm going to tell you that Sue has 2 hours to complete the trip. Find the speed of the car and the speed of the train. If she completes the trip in 2 hours. So first of all, we should only be focusing on positive speed and positive time. Negative speed and negative time don't make sense. So let's say 0 will be the slowest that she could go. And time, well, the smallest amount of time that it could take would be 0. But you'd have to be going infinitely fast for the time to be 0. So is she ever could it ever take 0 minutes to do the trip? No, even if she was going, 2,000 miles an hour, it's still not 0 time. It's quick, but it's not 0. So what happens to the amount of time it takes? Well, as she goes faster, the amount of time it takes gets less and less, but it will never reach 0. It can't take 0 minutes. All right. So there's the part of the graph we're going to focus on. And this part, we're just going to do graphically. Okay, I'm not going to do it algebraically because we're going to do a lot algebraically later. So let's just do graphic. I have to find how fast she would be going if it took 2 hours. So how do you think I can use the graph to do that? Okay, what are you looking for?
A value.
Yes, we are looking for a value. Yeah?
Is it when y touches 2?
It's when he touches 2. So I don't know if I went far enough to the right. I don't think I did. But we're looking for where the graph, I did, where the graph hits 2. Okay, wherever it hits 2, that tells us the speed of the car. So how am I going to do that on the calculator? Yeah.
Make a line y equals 2.
Yeah. If you want to know how fast to go to complete the trip in 2 hours, put a market at 2 hours. If it didn't quite hit it, which I think it does here, it's good enough. You could just go a little bit further to the right. All right. So we got a mark at 2, and now what we want to do?
Second count, intersect.
Intersect. So we have to pick a point on the blue, then on the red. Does the guess matter?
Kind of. Just want to be close.
Well, we want it to be close, but do they cross more than once?
No.
So you could really just enter where it is. If they only cross one time, the guess is going to give you the one you're closer to. So if it crossed again, then it would give us maybe a different one. But they only cross once. Yeah.
I was about to say, because there's 2 other lines in the back of it, isn't there?
Yes, since they're off the screen, it won't consider them. But yeah, if they were on the screen, those other 2, then yeah, putting a line at 2, it would cross this one as well. But the answer over here wouldn't make sense because that would be a negative speed. So we can't have negative speed. All right, so just hit enter. And I get 46.46. What is that? 46.46. It's what?
Speed of the car.
That's the speed of the car. So, speed of car is about 46.46 miles per hour. Oh, they didn't ask for the speed of the train. I thought they did. Well, what would be the speed of the train if they asked? Yeah?
66.46.
It'd be about 66.46 because it was 20 miles an hour faster. Yep. So you can see from the graph that at first it makes a big difference when she goes a little bit faster, but then eventually it doesn't matter as much. So like if she went 60 miles an hour, she wouldn't be getting the trip done that much faster because this curve is starting to flatten out. Wouldn't make as much of a difference. But early on, the speed made a lot of difference. Any question on that? All right, so that's an example of solving a rational equation. Right? That one we did on the calculator. So we didn't do it algebraically, so I'm just going to tweak this a little bit. When we start solving them algebraically, we're going to be multiplying both sides of an equation by a letter. So if you multiply So if you multiply both sides of an both sides, let me fix that. Sides. Well, I guess that's fine. If you multiply both sides by something that has a letter in it, comma, this may result in an equation that's not equivalent to basically what you started with. So if you, let me read that again. Period. You may have what's called an extraneous solution. So anytime you multiply both sides of an equation by something that has a letter in it, it can mess up your problem. There might be no way around it. You might have to do that. But you might get what's called an extraneous solution. An extraneous solution means it's an answer to the problem that you created by trying to solve it. It's an answer that was created by the process, but it is not an answer to the original problem you started with. So how do you eliminate extraneous answers? You basically should cross it out when you get to the end of your work. Well, you check it. You plug it back in, and you see if it works. If it doesn't work, you cross it out. Right. Let me give you have a real simple example of an extraneous solution. Let's say you have this equation. X plus 1 equals 3. Okay. If you solve that, what do you get? 2. Does everyone agree the answer to this problem is 2? Mm-hmm. Is there any other answer to that problem?
-4.
What?
-4.
4? Let's see. 4 plus 1. -4 plus 1 gives me -3. So is there any other answer besides 2? Okay, no. 2 is the only answer. Now, let's say you took that equation, and for some reason, which you don't have to do this here, but you're going to have to do it in this next problem, you multiply both sides by a letter. Let's multiply both sides by x. That's what you get if you multiply both sides by x. You get x squared plus x equals 3x. Now, when we solve a quadratic, we usually try to get it equal to what number? 0. How would you put that 3x on the left side?
Subtract it.
Subtract it. 3x subtracted to the other side. What's 1x minus 3x?
Negative 2x.
Negative 2x. Now, what do both of these terms have in common?
X.
Yeah, they both have an x in common. So let's take that x out. What would that leave you with in parentheses if you take that x out?
X plus x minus 2.
X minus 2. Now you factor it. What number could you plug in here to make that factor 0?
0.
And what number could you plug in there to make that factor 0? 2. How many answers did we just get to that equation?
2.
We got 2. And does everyone agree when I multiply both sides by x, did I do it correctly? So I started with the same problem. I multiplied both sides by the same thing, which you're allowed to do. But I ended up with this answer in addition to the 2. Does 0 work in the original problem? No. This is what we call an extraneous answer. The reason it happened is because you multiplied both sides by x. You didn't do anything wrong. You just created an answer that shouldn't have been there, and there's no way around it. So we have to check it in the original problem and make sure it works. That's all. Okay. Any question on that idea? All right, so let's try it. And the way that we're going to solve problems with fractions is we're not going to solve problems with fractions. We're going to try to get rid of the fraction. And I'm going to show you, I'll do it with numbers first, and then I'll do one with letters. So let's say you had something like this. 2 over 3 plus 5 over 4 equals, I don't know, x over 6. Actually, you know what? Let's see you do this. Make it 12. If I was going to solve that, I would want to multiply this, and that by something that would get rid of all those fractions. Does anybody see a number that you could multiply by? And 3 goes into that number, 4 goes into that number, and 12 goes into that number. Yeah. 12, exactly. If you multiply this by 12, this by 12, and that by 12, it's going to make all your fractions disappear. Now, did I multiply both sides by a letter? No, I multiplied by the number 12. So you don't have to worry about anything extraneous happening. There's no letter. We're just going to multiply. I would reduce first. 3 goes into itself once. How many times does it go into 12?
4.
4? 4 goes into itself once. And 4 goes into 12
3 times.
3 times. And 12 goes into itself once. And 12 goes into itself once. So let's look at what you're left with. What's 4 times 2?
8.
So we have 8 plus 5 times 3.
15.
Plus 15 equals, and what's left on the right side? About Billy Rose? What's on the right side? Yeah, on the right. What's left on the right side? Yeah, just x. So now we're basically done the problem once we add 8 and 15 together. That's a lot easier equation to solve than 2/3 plus 5/4 equals x over 12. Much easier because you don't have any fractions. Any question on what I did there? So that's going to be the same idea that we do with our problems. But instead of just having all numbers in the bottom, they're going to have some letters. Yeah.
I lost you after crossing you with the you crossed out 12 with 3s, 4s. I get those, but how did you correlate that to the 8 plus 15? I missed that.
So 4 times 2
Yeah.
plus
Okay.
5 times 3.
Yeah.
And then on this side, there's nothing left. It's just 1 times x over 1, which is just 1x divided by 1.
Which is x. Okay. Okay, I understood. Thank you.
Yep. So that's the goal. Try to get rid of the fractions, and the problem becomes a lot easier. And notice something else. This number times that number gave you that number. That's going to happen in most of the problems that we do. These two numbers will multiply to give you that one. Okay. All right, let's try this one. Okay, so with all those fractions, it makes it hard, right? That's a mess. So we're going to try to get rid of them. Before we do anything, let's factor that denominator. And just see if it comes out to something that's going to help us. When you factor this, what's the first term in each parenthesis?
X.
Yep, x. And you've got a minus in the middle and a positive at the end, which means, yeah,
Minus.
means minus, 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 minus. And two numbers that multiply to give you 3.
1.
Yeah. And that is how you factor it. And what do you notice about those two factors? They're the same as the other ones. Right? So that's what's going to make this easier. If it didn't work out that way, you could still do it. But we're not going to have any that don't do what I just showed. Okay. So last time, we multiplied everything by the product of this number and that number. We multiplied everything by 12. This time, you're going to multiply everything by that times that. So everything gets multiplied by x minus 1, x minus 3. First one. Second one. And the third one. And as long as you cancel first, it's going to be pretty straightforward. Look at just this part. Is there any common factor in the top and the bottom? And that's gone. Okay. Now look at the second part. Is there any common factor there?
X minus 3.
So that's gone. And how about the third part?
X minus 1, X minus 3.
Yeah, x minus 1, x minus 3, the whole thing. So all you're left with on the right-hand side now is 2. Now the left-hand side, what you're left with is the distributive property. 2x times x minus 3. What's 2x times x?
2x squared.
2x squared. What's 2x times negative 3?
Minus 6x.
Minus 6x. And you've got a distributive property in the middle. Make sure you grab this sign. This goes with the number. I know it's just a plus, but it could have been a minus, and then it would have been important. So plus 1 times x, just x, and plus 1 times negative 1, minus 1. And now that's our equation to solve. So it's a lot easier than what we started with. Because the highest exponent here is a 2, what kind of equation do we call that?
Quadratic.
It's quadratic. And what do we usually try to get a quadratic equal to when we solve it? 0. Yep. So I would put everything on the left side. So 2x squared. We can also combine like terms. What's negative 6x plus 1x?
Negative 5x.
Negative 5x. And how would you bring 2? Yep, subtract it. And you have negative 1 minus 2
-3.
gives you negative 3. Perfect. So now we're going to hope that that factors, and those will be our answers. So once you get that multiplication done and get rid of the fractions, then the rest of it is just factoring. Okay, what would be your first term? Here and then here.
2x.
Yep, you need a 2x and an x. What about your signs? You have a negative in the middle and a negative at the end.
Plus or minus.
You're going to need a plus and a minus. I would try it maybe like that. It does make a difference where you put it. If it's in the wrong spot, just switch it. And then 2 numbers that multiply to give me 3.
1, 3.
Yep. And I think putting them in that order, I think that's going to work. Let's see. So it gives you 2x squared. 2x times negative 3 is negative 6. X times 1 is 1. And what's negative 6 plus 1?
Negative 5x.
Perfect. That's exactly what we wanted. Okay. Now, once we factored it, what do we do with each of these factors?
And then we make it 0.
Yeah, find the number that makes them 0. So set that one equal to 0. Set that one equal to 0. And solve. What number would make 2x plus 1 0?
0.5.
1/2.
Yeah, negative 1/2. Yeah. And what number would make x minus 3 0?
3.
3. And those are our 2 potential answers. All we have to do is make sure that they work in the original problem. And usually the only thing you have to check is that they do not cause you to divide by 0. Right. Let's start with 3. Can't read the denominators, I'll just move this stuff away from them. If you plug 3 into the first denominator, what's 3 minus 1? 2. That's fine. If you plug 3 into the second denominator, what's 3 minus 3? 0. That's a problem. So 3 cannot be plugged back into this problem. 3 would cause you to divide by 0. So all we have to do is cross it out. And remember, we call that an extraneous solution. There's nothing you could have done to avoid it. It's going to happen. But you have to cross it out. If you got that far and you didn't cross it out, I'd probably just take like a point or 2 off, because I mean you did like 95% of it. You just forgot to cross it out by checking it. Okay, let's check negative 1/2. If you plug negative 1/2 in here, will you get 0? No, you have to plug in 1. If you plug negative 1/2 in here, will you get 0? No, you'd have to plug in 3. So all you have to do is check those 2, because this one is just the product of those 2. So negative 1/2 will work fine. And that's the only answer to this problem. So there's, yeah.
Will there always be one that's not right?
So I was going to say that there's 3 things that could happen. You can have one that works and one that doesn't. You can have both of them work. That's possible. Or you can have both of them not work. So it's possible you end up with a no solution. Yeah. 3 things that can happen. They both work. One works, one doesn't, but they both don't work.
So
And there's no way to tell until you do the problem.
So you were just saying, it's like just when the denominator comes 0, that's how you know it doesn't work, right?
Right. So before I even solved this problem, I could have told you right away, if you get a 1 or you get a 3, cross it. It would not work. Right. Same thing if I look at this one. If you get a 0 or you get a -2, I can tell you right away that those answers don't work because they would cause me to divide by 0. Okay. Any question on example 4? Let's try 5. Yep. And what I always want to do first is look at that right-hand side and factor it and make sure that it's the other two factors. This time it's not the two sets of parentheses. What can you factor out of here?
Sorry.
Yep, just x. And if you pull the x out, what are you left with inside the parentheses? X plus 2. Perfect. So this denominator is the product of those two. Yeah. Yep. Okay. So what are all three of these fractions going to get multiplied by? X plus 2. Yep. So x plus 2, x plus 2, x plus 2. And now cancel what you can first. Look at the first term. What do they both have in common?
X.
Yep. I'll cross it out in a different color. So x. That's cool. What does the second term have in common? X plus 2, x plus 2. Yep. And what about the third term?
These both cross out.
What's that?
They both cross out.
Yeah, the whole thing, right? This whole thing and that whole thing. So what's left on the right-hand side?
6.
Just -6. Usually that's what happens. The right-hand side turns into a number. And eventually we're going to add the 6 and bring it over. Okay, let's do the middle, just because that one's easy. All you're left with is +3 times x. What's 3x? That's the easy one. Now, what you're left with here is x minus 3 times x plus 2. Okay, so I'm going to do that kind of up here, and I'm going to write the answer. That we have to FOIL. What's x times x?
2x squared.
Just x squared. Yeah. And then x times 2? 2x. X times -3?
-3x.
And then -3 times 2?
-6.
-6. And then this is a plus, I should put the plus sign, plus 3x. Okay, well, what's going to happen on the left? Well, I see one thing that happens right away. Yeah, what happens when you do the -3x and the +3x?
Those cancel.
So those we can just cross out. And now we're left with x squared plus 2x. We have a -6, but we want to put that other -6 with it. So how would you move this -6 to the other side?
You got it.
You add it and watch what's going to happen here. What's -6 plus 6? 0. And then -6 plus 6? 0. So now we're left with something that doesn't have a constant, which means the factoring is simple. What do both of these have in common? Just x. If you factor out an x, what are you left with? X plus 2. What would you plug in to make your first factor 0? 0. And what would you plug in to make your second factor 0? -2. So those are the two potential answers. Let's look at 0. Can you plug 0 back into the original problem? Chris? No, you can't. You try to plug 0 in right here, you divide by 0. All right, so that doesn't work. Can you plug -2 into your first denominator? Yeah, that's fine. Can you plug -2 into the second denominator? No. So what happens here, that's an example where both answers don't work. That's a no solution. Sometimes you might see a symbol for that in math. It's like a circle with a line through it. Anyone ever seen that before?
Yeah.
That symbol, sometimes they write that for no solution. It's the only time in math I know of that we use a Norwegian letter. We use Greek letters a lot, like pi and stuff, but it's a Norwegian letter. Okay, so no solution. Right, any question on that one? Yeah.
How do you know that to give it x times x plus 2?
Because you always end up multiplying everything by this times that. That's how the problems that we're going to do are always going to work out. So it'll always be multiply everything by that times that. Let's see. And then that's the graphical. Oh, I'm going backwards. That's the last one. Okay. That was pretty much it for the equation. Does anyone want to see another one of those kinds of equations? We did 2 of them. Okay. All right, let's try this one. It says, using example 1, what possible rates could Sue travel at to ensure her trip is less than 2.5 hours? How is that different than saying exact 2.5 hours? What's the difference between saying she does it in exactly 2.5 hours versus less than 2.5 hours? Yeah?
It would be like one number, but like less, it could be like any number less than 2.5.
Right. It's going to be any speed, but then there'll be other numbers, either less than that speed or more than that speed. It doesn't have to exactly be a speed. It just has to be less than 2.5 hours. So I think we still have it typed in, hopefully. I think the window is going to be fine, but I don't want to put in a 2. What do I want to change that to? I want to change it to 2.5. So the line's going to be a little higher. That's how I know it's still going to be okay. All right. Now, if she can complete the trip in 2.5 hours compared to 2, how would you expect her speed to change? If she can take a little longer to do the trip. Yeah, she could go a little bit slower and still make it in time. So what do I have to find there first? Yep, find the intersect. Okay, so we've got the intersect. Now I want you to think about the speed she could travel at. If she goes exactly 34.88 miles an hour, she will complete the journey in 2.5 hours. It says she has to complete it in 2.5 hours or less. So what does that mean her speed could be?
Less than 34.88.
So she could go like a half a mile an hour?
Has to be more.
Has to be more, right? So she has to travel at that speed or faster. Yes, exactly. Some people mix that up. All right, so what does it say? Find the speed for her trip. So her speed has to be greater than. Is it greater than or equal to, or just greater than?
Greater than or equal to.
Does it say she can complete the trip in less than or equal to 2.5 hours, or less than?
Less than.
So then she has to be going faster than that speed. So she has to be going faster than 34.88. miles per hour. Okay, any question why it has to be greater than 34.88 and not less? If she goes less than 34.88, she's going to be going too slow. It has to be that speed, or it has to be faster than that speed. If it said she could complete the trip in less than or equal to 2.5 hours, then I'd be okay with the equal there. Yeah.
What reservation does she have that she has to be have to be at a place that specific time?
Well, this is more general. This isn't that specific. Maybe it's like, she has 2.5 hours before the reservation, before the check-in desk at the hotel closes. And if she's not there within 2.5 hours, she's not going to be able to check in. So then she knows, all right, 2.5 hours, I got to go at least 34.8 miles an hour. If she's driving 30 miles an hour and she's got 2.5 hours to get there, she's not going to make it. Yeah. Yep. So this one's a little more realistic because it's kind of open-ended. Just got to beat 2.5 hours. If it was exactly 2.5 hours, that's more unrealistic because why would you have to be there exactly 2.5 hours? Does the hotel care if you're 1 minute late or early? Not really. Okay. But if they close at a certain time, you got to make sure you get there. All right, so that's an example of an inequality. Okay, had a greater than, less than sign. So when we solve rational inequalities, we're mostly going to stick to doing it on the calculator. We're not going to be solving it the way I showed you with the equation, where you multiply everything by the LCD. Because if you remember, there's a certain time we need to flip the sign. Anyone remember?
What are you dividing by?
Dividing or multiplying. And with the method I showed you here, you're multiplying both sides by a letter. Well, I don't know whether that letter is positive or negative. So if I don't know if it's positive or negative, I wouldn't know whether I'm supposed to flip that or not. So that's why the method I showed you here doesn't work for inequalities. So we'll stick to graphing. Remember to always zoom in or zoom out because you can have hidden behavior that's off the screen. That first problem we did was perfect. I almost missed that hidden behavior, but I could just see that one pixel in the lower left that made me think something's happening there. So I got very lucky that I saw that. But you always should zoom out to check for hidden behavior. Again, we're not doing that because we're focusing on graphically. So any problem in the homework that's about an inequality, if it says to solve it algebraically, you can solve it graphically. The only ones you have to do algebra with are the ones that are equations. Okay, those are the only ones you have to do algebra with. Let me fix this. Okay, let's try this one. Okay, it's an inequality. So how are we going to solve it? Graphing. Yeah. The only thing you can mess up on here is just not plugging it in right.
Very real possibility.
Yep. What symbol do you think I'm going to have to make sure I use with the numerator and the denominator? Parentheses. Yep. So 2x squared plus 6x minus 8, and then divide by 2x squared plus 5x minus 3. And what am I going to put in y2? 1. So what I'm going to look for is where the blue graph is under the red graph. So just hit graph. We'll start with zoom 6. We might have to zoom out a little bit more. No, that's a pretty typical pattern. So there's nothing else hidden that you're going to see there. Okay. I'm going to look at this a little closer because it's hard to see. We're looking for where the blue graph is under the red graph. Well, first of all, is this U-shaped piece under the red? No. So we can ignore that. I need to see what's happening down here more. Okay, so let's adjust our window. I'm going to set it to go up to 1 for the y max. And I'm only going to go down to -3 because I know it just keeps dropping down. I don't need to keep seeing it go down. So let's just go to -3. And hopefully I can see in here a little bit better. Oh, probably shouldn't have done it right at 1. That was bad. Probably should go 1.5 because I don't want that line right on the very edge of the screen. Then it could be hard to see. Let's do 1.5. So now the line will be a little easier to see. All right. So it looks like that blue graph is going to be under the red graph in that entire area. Okay, I think it's going to be the entire area. Might look like it equals it on the right-hand side, but I bet it stays under it. Right? What's that?
No, just do it. I confused myself. I messed up.
It does go above it. It does go above it. It hits 1.01. Okay. And it hits it at 5. So that's where it crosses. It does cross it. I didn't think it was going to cross it. So it crosses it. 1, 2, 3, 4, 5. It crosses it right there. And if I keep zooming out, it would go above it. Yeah. Yeah. Any question on why the blue one goes above 1? I see it in the table. It goes above 1. All right. So let's see if we can figure out what's going on here. So I know I can't go past 5. I got to stop there. How far to the left does it look like I can go, and the blue one will stay under the red? Yeah, we could try, like, if you go to your table, we could try plugging in, like, -500. Yeah, we could plug in a big number and see. Yeah, it's still underneath. -200. Yeah, it's still underneath, 0.99. So if it's under at -200, it's going to stay under. So I can go as low as I want, and it'll stay under. And how do you represent as low as you want? Negative infinity. Now, we have to figure out how high we can go. What does it look like is happening to this blue line? What does it look?
It's dropping to infinity.
It's coming down, and it usually does that when it gets close to a what? An asymptote. Let's try -1, -2. To me, it looks like it's at -3. Let's try -3. If we get an error, then we know -3 is an asymptote. Perfect. So I can go as low as I want, right up to what number?
-3.
-3. Can I include it? No. If you try to include it, you're going to get an error. So you can't include -3. So that covers that section. Now we have to describe this section. What does it look like we also have over here? Another asymptote. I don't know. I'm thinking it might be like 0.5. Yep. You just try. I'm not going to give you one that's like 0.342. It's not going to be a weird number. It's going to be an easy number to figure out. So this asymptote is right at 0.5. So we can go from 0.5 up to, what number do we have to stop at?
5.
We have to stop at 5, and we can't include 5 because there's no equal to symbol there. So that's how you solve it graphically. Okay, you have to look for those vertical asymptotes. All right, and I had one more, but we can try that one tomorrow. We can do some from the homework as well. You could probably do that one on the calculator yourself. You just Y1, Y2, and then just look at the screen. What would make the denominator 0 in that case? 2. That's an easy asymptote to find. The asymptote's at 2. Okay, this one was a little harder. It's not as easy to see where it would be because it's a quadratic.
Now, could you just factor and then find it?
Yeah, you could have just factored it and found them that way too. I guarantee if you factor this, one of them is probably x minus, or actually it's probably x plus 3. So then when you plug in minus 3, you get 0.
On the test, like, if you gave us one like that and said like graphically find the asymptotes, and like if I tried to say skip the graphic and just factor it.
Yeah, you could skip doing the graph and just factor it.
Okay.
Yeah. I thought most people would find looking at the graph easier because then, then they can just guess. But if you want to factor it, you could have. Yeah. Okay, so that's the homework. So it's 1 through 13 odd, and then 20, 22, 24, 28, and 31. So I think it's like 12 or 13 questions. Okay, and we'll go over that tomorrow, and then we'll start to look at the last section for this week.